Welcome. Today's topic is vectors. This will be the first of a series of videos on vectors, so let me start with an introduction. Vectors are quantities that have both magnitude and direction. Types of vectors include displacement, acceleration, and forces, to name a few. By the way, quantities that do not have direction and only have magnitude or scale are known as scalars. Here are some examples. So let's talk about how we can represent these vectors. One way to do it is with directed line segments. Directed line segments begin with a point, P, and then a direction that extends for some length ending at a point, Q. We call P the initial point, and Q we call the terminal point. And the length of that directed line segment becomes the magnitude of our vector. Since we can use this symbolism, PQ, with an arrow over top of it, we always go to the right, we can use this symbolism to indicate the magnitude of that directed line segment. So up here, I could write that magnitude equals double bar, PQ, double bar. Now, to indicate our vectors, we do not always need to draw them. We can either type them into a computer, or we can draw the symbols ourselves. They'll look slightly different depending on how you are representing them. If you are representing two vectors, we'll call them vector U and vector V, in print, you will use the letter in bold. But by hand, that's kind of hard to do. So instead, we write the letter and put a little arrow over it. Okay, the arrow always goes to the right, just by convention. So there you have it in print and by hand. If you want to indicate the magnitude of vector U or the magnitude of vector V, you use the double bar with the bold letter if you're doing it in print. And then by hand, you just draw the double bar, the letter with the arrow, and the double bar on the other side. And that indicates just the magnitude of the vector. So there you can see how to indicate the vector and how to indicate the vector's magnitude. Now, here's a really cool thing about vectors. This vector U is exactly equal to this vector V. Now, I'll explain why that's cool in a little bit, but let's talk about when vectors are equal and when they are not. Vectors U and V here are equal because they have both the same magnitude and the same direction. So we could write that vector U equals vector V. However, vector W does not equal vector V or U, and it does not equal vector V either, because although vector U and vector W have the same direction, they do not have the same magnitude. Vector W is shorter, so its magnitude is less than that of vector U. Now with vector X, it may be a little bit hard to see, but the magnitude of vector X equals the magnitude of vector U. However, as you can see, these have very different directions. So vector X does not equal vector U. And then here's one more cool concept that we can show visually about vectors. Here is vector Z. It has the same magnitude as vector U, but it is going in the opposite direction. So in effect, vector Z is equal to the negative of vector U. Same magnitude in the opposite direction. So let me write out those details. Two vectors that have the same magnitude and direction are equal, and two vectors that are opposites have the same magnitude but opposite directions. So we could actually rename, if we wanted to, vector Z to be the opposite of vector U, or negative vector U, and we could call vector U the opposite or negative vector Z when it is useful for us to do so. Right now, I will just leave them as vector u and vector z going in opposite directions. But let's suppose you needed to show that vector u was equal to vector v. There are different ways you can do it. One way is to plot each vector on a Cartesian plane. So here they are, vector u and vector v. I have written down the coordinates of their initial point and their terminal point for each one. So let's figure out what the magnitude of vector u is. So the magnitude of vector u, well, look at this. If we go out horizontally from our initial point and down vertically from our terminal point, we have another right triangle, and we can use the distance formula to determine the magnitude of vector u. So in other words, the magnitude of vector u is equal to the length of the hypotenuse of the right triangle that we have just formed. And that can be simplified to 2 square root of 58. But we don't actually need to do that here, because watch what happens. The magnitude of vector v equals the difference in the x values plus the difference in the y values for vector v, and it turns out that the absolute value of vector v equals the square root of 232. So even without reducing, we can see that the magnitude of vector u equals the magnitude of vector v, which is fine, but that's only one thing we have to do to show that they're equal. We also have to show that they have the same direction. So let's move this over, and on the other side of the graph, I'll show that they do have the same direction. Because of the way that we have graphed these two vectors, all we have to ask is, are the slopes the same, or are the slopes equal? So does m sub u, vector u, equal m sub vector v? Okay, so what is the slope of u? The slope of vector u would be 10 minus 4 over 5 minus negative 9, or 6 over 4, which reduces to 3 over 2. That's really easy to do, so I went ahead and did it here. The slope of vector v would be 8 minus 2 over 6 minus 2, and we see at this point that the two slopes are equal, but I'll just go ahead and reduce it. On the left side of the graph, we showed that the magnitudes are equal. On the right side of the graph, we showed that the slopes are equal. Therefore, we can say that vector u is equal to vector v. We can also perform what is called scalar multiplication of vectors. Let's call this vector vector u. And let's play around with this a little bit. Let's take this vector and multiply it by 3. So I have my first vector, and then I have a second vector going in the same direction with the same magnitude, and I have a third vector with the same magnitude and the same direction. And if I put them tail to tip, I now have a vector that is 3 times as long as my original vector, or another way to say it is I have a vector of 3 times the original magnitude. If I had taken the original vector and multiplied it by a -2, the -2 would have changed the direction to its opposite and extended the magnitude by 2. We can call the new vector vector w, and its magnitude is equal to 2 times the magnitude of vector u, only it is in the opposite direction. To be exactly precise with our wording, this is how we put it. If we have a real number k and a vector v, then k times vector v has a magnitude of the absolute value of k, times the magnitude of vector v. And k times the vector v has a direction the same as vector v if k is greater than 0, or positive, and opposite that of vector v if k is less than 0, or negative. So, to be completely precise in my notation, I'm going to go back to what we were doing with our vector u and v over here. More precise notation would not be just 3 times the magnitude of vector u, but it would be the absolute value of 3 times the magnitude of vector u equals the magnitude of vector v. Likewise, over here, where I was dealing with vectors u and w, and I multiplied vector u by -2, the magnitude of vector w would be the absolute value of -2, which is +2, times the magnitude of vector u. So yes, the magnitude of w has the same value as it had before. The negative just reverses the direction. And since all I am dealing with here is magnitude, it is the absolute value of -2 that we multiply by the magnitude of vector u to get just the magnitude of vector w. The direction is changed, though. It's the opposite. This will become important when we add and subtract vectors. So, let's add these two vectors, vector u and vector v, represented by these lines. Here's the initial point for vector u, and we're going to take vector v and put the tail of vector v at the tip, or the terminal point of vector u. And now that we have done that, our resultant vector stretches from the initial point on u to the terminal point on v. So we can say that vector u plus vector v is represented by that green arrow. Also, it does not matter in which order you add. If you start with the initial point of vector v and add vector u to it, we get the same resultant vector because it has the same magnitude and the same direction. Both of those forms are equal. We can also subtract vectors. So let's look at vector u minus vector v. And that can be rewritten as vector v plus the opposite of vector u. So let's see what that looks like. Here's vector v, and here's vector u, but we want the opposite, or negative vector u. So when we put the tail of negative vector u, we get the resultant shown there in a thicker line and a green line. It is vector v minus vector u. So now it's time to add some new notation. Here is vector I, and as you can see, I've put it on a grid, so it looks like I is 1 unit in the x direction, on the x-axis. If that's the x-axis, up here is the y-axis, and we can draw a 1 unit vector going in the y direction, j. In fact, j is called the unit vector in the vertical direction, and we let I, vector I, represent the unit vector in the horizontal direction. Now, in your book in Pearson, once again, you will just see the I and the j as bold characters. I will try to remember to write them with the arrow on top to indicate that they are unit vectors. So now it's easy to recognize that we could go 2 units in the I direction to produce a vector of length 2 times the unit vector, or 2i, and we could produce a vector in the vertical direction that is the length of 4j. So let me now, since those look a little bold, but I am doing it by hand, let me make those into arrows. So vector 2i and vector 4j. So let's put those unit vectors to work. Here I have a vector with an initial point at the origin and a terminal point up here. So where is my terminal point? Well, first I'm going to let this be vector, I don't know, vector W. Okay? And in the x direction, I can go out this way to form a right triangle. 1, 2, 3, 4, 5, 6. 6 unit vectors in the horizontal direction, or 6 times vector I. And I can go up, how far? 1, 2, 3, 4, 5 times vector j. So I have this vertical component of my vector w, and I have this horizontal component of my vector w. When I add them together, I get a right triangle, and I can do some calculations now. And in fact, those unit vectors define vector w. Vector w is 6 times vector I plus 5 times vector j. It is the resultant of adding the two vectors that I drew there in I and j. Now we can determine the magnitude of vector w. So the magnitude of vector w, once again we would use the distance formula, but now we already have the distances. The distance in the horizontal direction is 6. We're going to square that. The distance in the vertical direction is 5, and we're going to square that. So we get the square root of 36 plus 25, or the square root of, 1161, which is as far as we can take that without a calculator. But let's make this a more general statement. For any vector, you can find a horizontal component, A, times the unit vector, and a vertical component, B, times the unit vector, so that the vector could be expressed as A times the unit vector I plus B times the unit vector J. And to calculate the magnitude, you would take the square root of A squared plus B squared. That's the general form. Will it work if A and B are negative? Let's take a look. Let me leave this general formula with this triangle in the first quadrant, and I will draw another vector in a different quadrant. Let's take a look at vector z, which is drawn in the third quadrant. Vector c may be said to be composed of this horizontal vector, which is equal to -3 times the unit vector I, and added to that this vector, which is equivalent to -4 times the unit vector j. So we could say that vector z equals -3 times the unit vector I plus -4 times the unit vector j. Or sometimes we just, for shorthand, say -3i minus 4j. And what is the magnitude of vector z? Well, let's write it out. The magnitude of vector z. There's the symbolism. It's going to be the a value squared plus the b value squared. Now, those are both negative. However, magnitudes are always positive. So the magnitude of the I vector plus the magnitude of the j vector gives us that. So square root of 9 plus 16 equals square root of 25, or 5. The magnitude of vector z equals 5. Question: if I had kept the negatives, would my magnitude of vector z been different? Answer: no. And now back to your regularly scheduled video. We have a 3, 4, 5 triangle. Notice there is no I, no j, no z, no nothing over here. That is just a magnitude. And as added bonuses, we can say the magnitude of the vector -3i equals 3, and the magnitude of vector negative j equals 4. This video is long enough. I'm going to end it here, but I will be producing a second video, video B, on vectors. So stay tuned and practice the problems that you know how to do so far.